Hello, and welcome to Zetec's webinar on advanced focusing techniques for improved inspection capabilities. My name is Wayne Waxman, and I'm the Director of Marketing here at Zetec. I'd like to thank everyone for joining us today. I do have a couple of logistical items before we get started. Everyone is in listen-only mode, and we are recording today's session so you can review and listen to it or share with your colleagues in your organization. Everyone who registered for this webinar will receive an email later this week with a link to the recording. Finally, there will be a Q&A session at the end of this webinar, but you don't need to wait until the end to send in a question. At any time, just type your inquiry in the questions section on the GoToWebinar panel you see on your screen. Before we begin the webinar, I would like to give a quick overview of Zetec. Zetec is a global NDT leader. For over 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies, setting new heights in inspection performance, productivity, and predictability. Zetec's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, and oil and gas. Zetec is a subsidiary of Roper Technologies. Let's get to today's session, which will be presented by Guy Maas. Guy has been involved in advanced UT method development and implementation, capability assessment, and software development for more than 25 years. Since 2000, Guy has held various positions at Zetec and RD Tech, including Sales Director, Product Manager, and UT Applications Manager. Guy is currently the Sales Engineer Director for UT at Zetec. With that, I'd like to now turn this webinar over to Guy.
Thank you, Wayne. Hello, everybody. I'm Guy Maas, and I have the pleasure of presenting this webinar on FMC and advanced focusing techniques for improving phased array UT inspections in various industries. This is the agenda for today. First of all, I will do a short historical recap on the introduction of portable phased array units in the industry. Then I will review the principles of the full matrix capture, or FMC, data collection process and some advanced focusing techniques like TFM and STF. I will then present Zetec's newest portable phased array unit that offers this new technology, in addition to all the features required for best-in-class PAUT and TOFT inspections. After that, I will show live UT imaging on a reference block to illustrate the benefits of FMC and advanced focusing techniques, and also the conditions required to exploit the full potential of this new technology. The second part of this webinar will address some of the case studies that we performed using FMC and advanced focusing techniques. We will introduce the challenges of each inspection configuration, look at the experimental results, and point out the potential improvements of the new technology. And finally, we will wrap up with some conclusions from the presented material and, of course, take your questions. The introduction and adoption of portable phased array UT units has been a leap ahead for ultrasonic inspections of critical components in various industries. Over the last 5 years, several manufacturers have developed systems that offer far more power and performance than first-generation units that came on the market in the early 2000s. Larger data file size, better amplitude resolution, faster data acquisition rate, and advanced onboard data analysis. Due to the improved efficiency in preparation, acquisition, analysis, and reporting of inspections, and to the availability of software tools that ensure code compliance, it's fair to say that phased array UT is now a mature and industrially proven technology. The next technological step in ultrasonic phased array examination involves full matrix capture and advanced focusing algorithms. But before diving into this new technology, let us briefly review how standard phased array works. Phased array technology uses multiple independent UT transmitting receiving channels. The signals of the individual elements of an array probe are pulsed and received using focal laws or delay laws, and are then summed to generate a single A-scan signal for each beam. The set of summed A-scans can typically be a sectorial, linear, or compound sweep. For standard phased array, it's important to keep in mind that only the summed and digitized A-scan signal is transferred to the computer for display and recording, while the A-scan signals from the individual elements are lost. This slide shows how it works in practice. The probe is positioned on a specimen, and the phased array equipment generates a group of summed A-scans that are displayed as a sector scan image with a range of beam angles to cover the volume and to detect the reflectors. This image is shown live on the screen of the unit and can also be saved during inspection. After recording, we can apply processing, for instance, volumetric merge, but we cannot create additional focal laws. With the full matrix capture or FMC technique, the elementary A-scan signals from every transmitter-receiver pair are captured and recorded. Like the image on this slide shows, the elements of the probe are pulsed one by one, and for each pulse, the reflected signals are received on each element. At the end of the sequence, for a probe with 4 elements, a matrix of 16 A-scan signals is recorded. For a more realistic situation, a probe with 64 elements, we will have a matrix of 4096 A-scans. From the raw A-scan signals, it is then possible to generate UT images for any given focal law in terms of aperture, angle, or focus depth, and for advanced focusing techniques through post-processing and recently also live during inspection. Indeed, the underlying mathematics for the processing of FMC data was described more than 10 years ago. But in recent years, a drastic increase in processing power allows to perform the summing operations while the probe is moving over the component. So the time-consuming storage of elementary FMC data can be avoided, and the resulting inspection speed becomes comparable to standard phased array. The most commonly used advanced focusing algorithm is the total focusing method, or TFM. This animation explains how it works. The TFM algorithm sums the elementary A-scan signals from all elements in the array to generate a frame of pixels, where each pixel is computed using a dedicated focal law. The TFM frames can be used for live interpretation, or they can be stored for each position of the probe, very similar to a dynamic merge view in regular phased array. In theory, ideal focusing is achieved in each point of the frame. But I will show later that the focusing capability of the technique still depends on the acoustic wavelength and the total aperture of the array. Therefore, some conditions must be met to effectively obtain ideal focusing. The elementary A-scans from the FMC data recording can also be used with an alternative processing method to generate a sectorial sweep of A-scans while focusing in each point along the sound path. We will call this technique sectorial total focusing, and its physical principle is very similar to a DDF or dynamic depth focusing algorithm, applied both in transmission and in reception. Again, the operator can perform online data interpretation, or the images can be recorded during an encoded inspection sequence. The algorithm has the benefit of recording a summed A-scan signal for each angle, very similar to standard phased array, and this might facilitate its acceptance in codes and standards. Let me now introduce Zetec's latest hardware innovation in phase array UT. At the end of last year, we launched the TOPAZ 64, a high-end, fully integrated portable unit. It has a 64-128 PR phase array configuration that allows for two-side inspection of thick welds with 64-element active aperture probes. This and the two separate conventional TOF channels at 200 volts make it a best-in-class inspection system for code-compliant weld inspections using simultaneous phase array and TOF. But in addition, the TOPAZ 64 also offers best-in-class live high-resolution TFM and STF. The TOPAZ 64 allows to perform an encoded scan, motorized or manually driven, and records live TFM frames or STF sector scans at each position, just as we record sector scan images in standard phase array. After the recording, the TFM is available as an actual merged data group in UV Touch, and the STF data can be exploited like a standard phase array sector scan. In addition to the typical square pulse, 75 volts on 50 ohms, the system can also generate a bipolar pulse, 150 volts peak to peak on 50 ohms, with 40% more acoustic energy. Obviously, this contributes to the overall signal-to-noise ratio of the ultrasonic signals, either standard or generated from elementary A scans. The unit is also capable of saving the raw FMC data for post-processing in UltraVision Classic. And like the other TOPAZ units, the TOPAZ 64 is controlled by the industry-proven embedded UltraVision Touch software. Before looking at real flaws in the case studies, let me start by illustrating the benefits of advanced focusing techniques and the key parameters that allow to exploit the full potential of this new technology. I will use the well-known ASTM E2491 phase array reference block with different sets of side-drilled holes, and a typical 5 MHz linear array probe with 64 elements coupled to an L-wave wedge. We are looking at ultrasonic images of a set of 1 mm diameter side-drilled holes located on a vertical line. Two channels are shown simultaneously on the TOPAZ 64. On the left side of the screen, we have a high-resolution TFM frame, 512 by 512 pixels, generated with the complete 64-element aperture of the probe. The calculator in UV Touch shows the coverage of the frame relative to the specimen and makes it easy to set and adjust the parameters of the frame. On the right side of the screen, we have a standard phase array sector scan showing angles between 20 and 70 degree L waves and a resolution of 0.5 degrees. Again, the complete 64-element aperture is used. The standard phase array channel is focused in projection mode, just in front of the wedge. In the starting position, we can see that the TFM algorithm, in combination with the large aperture of the probe, allows for ideal focusing on all reflectors. At this specific probe position, the standard phase array sector scan is also well focused on all reflectors and shows a similar, nearly perfect image. When we start moving the probe by roughly 10 millimeters in one direction or the other, we can observe that the image provided by the standard phase array technique shows defocusing on most of the reflectors, simply because the sound field is focused elsewhere. On the other hand, for the TFM technique, nearly ideal focusing is conserved over a large range of probe positions. This clearly illustrates the capability of TFM to focus in the complete region of interest and not only on a predefined locus. I have now replaced the TFM channel on the left side of the screen by an STF channel with the same angle sweep as the standard phased array channel. And we perform the same test again, starting from the ideal position for the standard phased array and moving the probe away from that position. And very similar to the live TFM technique, the live sectorial total focusing technique conserves nearly ideal focusing over a large range of probe positions. As previously mentioned, the active aperture of the probe is a key parameter for the focusing capability. This slide clearly illustrates the influence of this active aperture on the TFM imaging. Live TFM images of the same set of side-drilled holes were recorded with different apertures. From left to right, 64, 32, and 16 elements of the probes were used to generate the TFM frames. The images show that a large aperture is required to fully benefit from the focusing power of the TFM algorithm, and the same can be demonstrated for the STF. Indeed, even when advanced focusing algorithms are applied, the focusing capability is still limited to the near field of the probe. And this near field can be increased by selecting a probe with a larger active surface or a probe with a higher frequency. Let us now look at the influence of the TFM frame resolution on the detection capability and the reliability of the inspection. We start from the same setup that we used a few minutes ago, showing a TFM frame of 512 by 512 pixels. We can see the TFM frame on the left side of the screen and the amplitude depth curve on the right side of the screen. This curve is like the A-scan signal of a virtual 0-degree probe in each horizontal position of the TFM frame. The different echoes represent the responses from the side-drilled holes, and we can see a regular sensitivity distribution. If we go into the TFM calculator, we can see how to define and adjust the frame by defining the frame start and frame extent horizontally and vertically. The frame resolution will determine the depth and the width of the individual pixels in the frame. Let us now change the frame resolution to 128 by 128 and look at the image again. The TFM image has a very different aspect now. It looks pixelized. Also, the A-scan signal on the right shows irregular amplitudes for the echoes from the reflectors. When moving the probe very slightly, actually less than a millimeter, we can observe random and important variations in the echo amplitudes, as if some reflectors are disappearing and reappearing. The pixelized aspect of the TFM frame can be improved by applying the smoothing feature available in UltraVision Touch, but the important amplitude variations remain. Obviously, an actual inspection with these parameter settings would be very unreliable and could leave flaws undetected. The TFM calculator in UltraVision Touch helps the operator understand and avoid this potential issue. We can see that the pixel size for a 128 by 128 frame is as large as 4/10 of a wavelength. Using the wavelength as the unit for the pixel size may seem a little strange at first, but it avoids the UT operator having to calculate the wavelength for each of his probes and wave modes. From a physical reasoning, similar to the Nyquist or sampling theorem that the ASME code uses to determine the recommended digitizing frequency for standard UT and phased array inspections, the maximum possible amplitude error for a TFM frame can be calculated. We have implemented this principle in our software to automatically calculate the amplitude fidelity parameter to help the operator set up TFM configurations for reliable detection. For the given frame size and 128 by 128 resolution, we can see that the parameter is at almost 10 dB, which explains the important amplitude errors that we previously observed. If we go back to a 512 by 512 frame, we can see the pixel size reduced to a tenth of a wavelength, and the amplitude fidelity improved to less than 0.5 dB. Obviously, this setting results again in the initial high-resolution TFM image. In the various working groups on the codification of FMC and TFM, the discussion about recommended pixel size is still ongoing, but at this time, an amplitude fidelity of 2 dB or better is considered a good compromise between reliability and inspection efficiency. I think this simple experiment clearly illustrates the importance of the TFM frame resolution, especially when inspecting thicker components. Let us now move on to the case studies. In the first case study, we will evaluate the performance of the TFM technique on hydrogen-induced cracking. This is a common type of damage occurring in wet hydrogen sulfide refinery process environments, even at relatively low temperatures. Hydrogen-induced cracking is a kind of blistering damage that tends to form parallel to the surface. It becomes really damaging when it becomes extensive, or when it gives rise to cracking that propagates into a weld, or when it begins to go stepwise through the wall. The considered specimen is about 1.5 inch thick and has strong hydrogen damage around mid-wall. The typical blisters connected by stepwise internal cracks. A 10 MHz linear array probe with 64 elements was used for the examination, in direct contact with the specimen. This slide shows the UT images of the damage inside the specimen. On the left side, we see the image from a compound scan technique using L waves ranging from -15 to 15 degrees and an aperture of 32 elements. On the right side, we see a TFM frame with 512 by 512 pixels, covering the same volume of the specimen. The damage in this specimen is so extensive that standard phase array has no difficulty detecting. Indeed, the different blisters, essentially perpendicular to the ultrasonic beams, are very good reflectors. But the raw sector scan doesn't show the complete detail of the damage. The data from the live TFM inspection provides a more accurate image of the stepwise internal cracks that connect the adjacent hydrogen blisters. In this case, the superior imaging of the TFM technique is obtained by the better focusing capability, but also because the original FMC data recording includes signals from a multitude of insonification angles on the reflectors that compose the damage. High temperature hydrogen attack, or HTHA, is another hydrogen-related damage mechanism. This problem concerns steels operating at elevated temperatures, above 400 Fahrenheit, in hydrogen environments in refinery, petrochemical, and chemical facilities. HTHA is the result of hydrogen dissociating and dissolving in the steel, and then reacting with the carbides to form methane, which cannot diffuse out of the steel. The methane accumulates at grain boundaries and eventually leads to the fissures and cracking typical of HTHA. Early stages of HTHA are very difficult to detect because of the small size of the voids, typically smaller than a tenth of a millimeter. The considered specimen contains important HTHA damage at the depth of roughly 3 inches. The same 10 MHz linear array probe from our first case study was used. This slide shows the recorded TFM data on the specimen, again with frames of 512 by 512 pixels. We can observe that the high frequency probe, in combination with the TFM focusing, allows to detect reflectors several times smaller than the wavelength. Industry experts consider that the excellent focusing capability of TFM is an important tool for earlier detection and better characterization of HTHA. Still, in view of an efficient and reliable inspection strategy for this damage mechanism, TFM is likely to be combined with other ultrasonic techniques like TOFT. With TOPAZ 64, all required techniques can be implemented on the same portable unit. The next case study will illustrate the flexibility and the performance of TOPAZ 64 and Ultravision Touch in using live TFM for weld inspection. For our trial, we have a carbon steel weld specimen with a wall thickness of 19 millimeters or 3/4 of an inch. It contains typical manufacturing flaws: lack of fusion, incomplete penetration, a toe crack, and a cluster of porosity. The weld will be inspected with TFM from both sides in a single scanning sequence. Live TFM frames are generated from two 5 MHz 64-element linear arrays on shear wave wedges. When performing shear wave inspection with the weld cap in place, the second half skip is typically used to cover the examination volume. This is why we have selected the TT-TT wave mode for generating the TFM frames. The Zetec weld crawler is used to carry the probes for this one-line scanning sequence. But the TOPAZ 64 and the onboard software also integrate smoothly with other encoded and motorized scanning mechanisms. In this case study, only the live TFM frames are recorded. No raw FMC data will be stored. This allows for a scanning speed around 25 millimeters per second, while recording frames every millimeter. This is only slightly slower compared to two-sided standard phase array with similar inspection parameters. The live TFM data file size for this type of weld is around 350 megabytes for a weld length of 1 meter. This is roughly double the size of the standard phase array. After recording, the Ultravision Touch software can be used to review the data, either on the TOPAZ 64 unit or on a separate computer. Upon loading the data file, we get an overview of the two TFM channels for upstream and downstream. By moving the data cursor along the scan axis, the 4 manufacturing flaws are clearly detected on the TFM frames. Since each of the TFM data groups includes full volumetric data, we can also use the projection views for efficient analysis of each indication and for flaw characterization and sizing. The recorded TFM data groups have exactly the same format as the results from a volumetric merge operation. It is easy to use the projection gates to isolate and visualize individual flaws, like the near surface toe crack with well-resolved corner and tip signals. We can also observe the capability of the TFM technique to provide better resolution for imaging the cluster of porosity compared to standard phase array. Let's now move on to a case study performed to explore the potential of advanced focusing techniques on thick carbon steel vessel welds, let's say from 3 inches and up. We know that code-compliant phase array UT and TOFT can provide adequate detection, but the characterization of deeper indications can be sometimes challenging. The considered specimen is a thick carbon steel weld containing real flaws, a rough crack, and a cluster of shrinkages, located at different depths in the weld. The same 5 MHz linear array probe and shear wave wedge from the previous case study were used. We can see from left to right on this slide TFM and STF images that were reconstructed offline from raw FMC data recorded during scanning of the weld, and a standard phase array sector scan recorded during the same scanning sequence. The standard phase array channel was focused at a sound path of 50 millimeters. The active aperture is 64 elements for all techniques, and adequate resolution was used. We can see that the rough crack at shallow depth is well detected by all techniques, but an important improvement can be observed in the imaging of a cluster of shrinkages around 3 inches of depth. The standard phase array technique is not adequately focused in this range, so flaw characterization is very challenging. On the other hand, the images generated by the TFM and STF algorithms are totally focused over the inspected depth range and provide a high-resolution image of the deeper flaw as well. My last case study for today is about inspection of dissimilar metal welds, or DM welds. These welds typically join 2 or more different materials and mostly involve Inconel alloys. They are often used to connect internally clad carbon steel vessels to stainless steel piping. The image on this slide shows a typical dissimilar metal weld configuration. Dissimilar metal welds are very challenging configurations for UT examination due to the various propagation issues in austenitic structures, the presence of multiple acoustic interfaces, and the sometimes very complex geometry, including conical nozzles and tapers. Around the year 2000, a new damage mechanism called primary water stress corrosion cracking, or PWSCC, was encountered in nuclear plants all over the world and led to the development of advanced phased array inspection procedures for dissimilar metal welds. Zetec collaborated with EPRI in 2005 to formally qualify the first phased array procedure for in-service inspection of dissimilar metal welds. Qualified inspection techniques for DM welds are typically based on 1.5 MHz dual 2D matrix array probes, generating L waves for better propagation in the coarse grain austenitic material. The dual transmit-receive configuration offers better sensitivity and signal-to-noise ratio due to the convolution of transmitter and receiver beams, and avoids ghost echoes caused by internal wedge reflections. In our case study, we used a dissimilar metal weld practice specimen made available by the EPRI NDE Center in Charlotte. The specimen has a wall thickness of 1.2 inches, and it contains a large branched ID surface breaking crack. The qualified techniques have no problem detecting this large flaw, but the objective of our trial was to explore the potential of advanced focusing techniques for improving flaw characterization and sizing. For this purpose, we used a recently designed large aperture DMA probe at 1.5 MHz. Both transmitter and receiver arrays have a 10 by 6 element configuration, and this probe assembly can be driven by the TOPAZ 64 system. The image on this slide shows the acoustic beam for standard phase array focused near the ID surface and the intended morphology of the branched ID crack. For this laboratory study, we decided to record elementary FMC data together with a standard phase array channel set up according to existing best practice, with L-wave beams from 35 to 70 degrees. The probe I just discussed was used at full aperture for the 2 techniques. We will use the UltraVision Classic software to review the data and to perform post-processing of the raw FMC data with different advanced focusing algorithms. So let us first look at the recorded data from the different techniques. Here we see the standard phase array data, and when we move the data cursor to the zone of the flaw, it becomes visible on the sectorial scan at the bottom right of the screen and on the A-scan signal just above. As I mentioned in previous webinars, the volumetric merge tool facilitates efficient data analysis and flaw evaluation. The merge operation has already been performed in this case, and this is how the merged data from the standard phase array looks like. The corner trap of the large crack is very well detected because the lower angles of the sector scan are typically focused near the ID. The upper part of the crack is visible and can be enhanced by using some soft gain, but the image is incomplete for this very high crack. Like I said, we also recorded elementary FMCA scans, and in the raw form, the data looks like this. Obviously, these signals cannot be interpreted by the human mind, so processing is required. The advanced calculator in UltraVision Classic has all the tools to facilitate this process. We need to select the TFM Pitch and Catch option in the Probe tab and then go to the TFM tab. Very similar to what we saw in UltraVision Touch, the TFM frame is defined by its horizontal and vertical start and extent, and by the pixel count. With this low frequency probe, a 256 by 256 frame will be sufficient to obtain good amplitude fidelity. And now we can hit the process summation button to start the TFM reconstruction algorithm. For better comparison, I will show the merged data from the standard phase array on top of the screen and the processed TFM data at the bottom of the screen. We can see that the image of the corner trap is almost identical, but we now get a complete image of the upper part of the crack. These signals allow to size the crack accurately within less than a millimeter of its actual through-wall size. Also, some other facets of the branched crack clearly stand out from the ultrasonic noise. We have also used the STF algorithm to process the same FMC data, this time generating a totally focused sectorial scan from 20 to 80-degree L waves. I will now show this data on top of the screen instead of the standard phase array. And we can see that the results of TFM and STF are very similar. This last case study has shown that the FMC data capture technique can also be applied with dual 2D matrix array probes. Also, we have seen that TFM and STF images reconstructed from elementary A-scan signals can provide good ultrasonic data through attenuating materials and have the potential to improve flaw characterization and sizing. From all the information and the various case studies presented in our webinar today, we can draw the following conclusions. Advanced focusing techniques are a promising additional tool in the phase array UT toolkit. They can improve the resolution of flaw images and increase the inspection coverage with focused beams. Active aperture and frame resolution are key parameters and must be carefully selected to exploit the full potential of the technique. Selection of appropriate probes in terms of frequency and wave mode remains a mandatory requirement for successful inspections. In the framework of regulated inspections, code-compliant phase array and TOF techniques can be complemented with TFM for flaw characterization. Zetec's new TOPAZ 64 offers industrially proven phase array UT and TOF, fast, high-resolution live TFM, and raw FMC data saving in a single, fully integrated portable unit. This concludes the presentation part of the webinar. We will now take some time to answer a few questions that have been received since the start of our webinar.